Hi, I'm Yobi, and I'm going over how to find the determination of a concentration of a weak acid that we did in lab last week. And we did this by titration. And what titration is, it's used to find a concentration that you don't know by using a concentration that you do know. And it's performed with a burette, so the volume is known, and you can calculate it by doing that. The purpose of this lab was to calculate the molarity of an unknown acetic acid, and then to find the standard deviation of this molarity. The balance equation with NaOH was KH C8H4O4 NaOH, and that yields KNaCH8H4O4 plus H2O. And to start, we had the mass of the KHP for 3 trials. And we used the burette for titration, and here's the volume that each of them led to. To find the molarity of the NaOH for trial 1, we took the mass of the KHP for trial 1 and divided it by the total mass and got the molarity for KHP. And then we took that molarity that we just found and used the 1-to-1 stoichiometric ratio that we found in the equation that we made to find the moles of NaOH. And then we divided the moles by the NaOH by the liters of NaOH we added during titration. And I found the molarity of NaOH for the first trial to be 0.095 molar. Then here's a chart of all the molarities that we found. There's just the equation's not there for them. Then we added up 3 of the closest ones and divided by 3 to find the average. And I found the average molarity to be 0.09467. To find the standard deviation, we had this equation to start with, and we filled in each x 3 different times and subtracted by the average and squared it to get this answer here. And we divided by 2 because n equals 3 and then minus 1 is 2. And our standard deviation was 5.77 times 10 to the negative 4th. And I had acid unknown number 86, and we used the volume of this 10 milliliters for each trial, and here's just a chart of the burette readings. To find the molarity of this unknown acid, we took the liters that we used and multiplied by the moles that we found earlier in the experiment. And then once we had the moles, we did the stoichiometric ratio to find the moles of the H+, and then divided by the unknown acid, the liters of the unknown acid that we used. And I found the molarity of this acid to be 0.15 molar. And here's just a chart of each of those molarities for each trial. And to find the average molarity of each trial, I just added up the 3 closest ones and divided by 3 and got 0.149 molar. And then I did the standard deviation for this equation as well, and I found the standard deviation to be 0.0026. For the discussion, what would happen if it was a contaminated substance? If it was a contaminated substance, the NaCl of the molarity would be higher than it should be because the NaOH absorbs water from the air and would cause the molarity to be, the mass to be higher than it should, which causes the molarity to be higher than it should. And this would affect the unknown acid in the same way because the numerator would have been higher than it should have, which caused an inflated numerator and molarity. Why did we titrate instead of weighing out the NaOH solid? Even though it's quicker just to weigh out the NaOH solid, it's less accurate. This ensures that only the NaOH is being weighed and not the water vapor as well, and it's easier to have a small amount of excess possible in the experiment. We had to create a reaction for sodium bicarbonate and hydrochloric acid, and when you balance the equation, that's what it looked like. We took the grams of Na2CO3 and divided by the total mass of the Na2CO3 to find the moles of the Na2CO3. And then we took that answer and multiplied it by the stoichiometric ratio to find the moles of the HCl. And once we had the moles of the HCl, we used the liters of the HCl that was used in the lab and found the molarity of HCl, and I found that to be 0.112.